Hello, welcome back. So, I'm about to get into chapter 16, so we're skipping over several chapters here to get to another group of biomolecules. Um, just to let you know, my setup right now, I'm surrounded. Got my iPad, got my notes, got my book, got my computer that has the full PowerPoint open on it. I'm also here with a very, very clingy little cat. So my cat is here. I'm alone with him, and he hasn't seen me much of the day. So he is like thirsting for attention. So um, if you hear me talking to my cat, or if I have any awkward pauses or shifts or anything, I apologize for that. That's most likely because of this feline up here. So um, you remind me, I'll show you a picture of him someday. He's an adorably sweet cat, but he is being a little annoying right now, so I apologize. Nevertheless, we will press on and see how we can do. So, chapter 16 is all about carbohydrates. And so, the first thing to look at here is actually some of the terminology. What is a carbohydrate? You've heard of this, I'm sure, many, many times in your life. Carbohydrates, they're basically sugars, right? Various types of sugar. So those two terms are synonymous. They're also synonymous with the term saccharide. So any one of those terms any one of those terms in biochemical, parlance basically means the same thing. So we'll probably be using the term saccharide more than any other. All right. So this chapter is going to be discussion of saccharide sugars, the various types that exist, the various structural features, and they do have their own unique structural features and linkages, and also some of the applications in which we see them. All right. So again, first off, terminology. We talked about the word saccharide. Just like with peptides, we can use some prefixes here to sort of describe how many links in the chain that we have. Right. A monosaccharide is just going to be one singular sugar unit, right? One molecule of a carbohydrate. A disaccharide, much like a dipeptide means two amino acids are linked together, a disaccharide means you have two sugar units. These can be two of the same type of monosaccharide, or they could be two different ones, right? So just like with amino acids, you can have a lot of variety in terms of what gets linked to what. You kind of enter this little gray area where you have something called an oligosaccharide, right? So we could keep going. Three sugar units is a tripeptide, four is a tetrapeptide, et cetera, et cetera. If you have 10, 12, 15, whatever, that's generally an oligosaccharide. But when you start getting into the hundreds, much like with amino acids, that's when you start forming a polymer. You have a really, really long molecular chain. And so when there's lots of sugar units linked together, that is called a polysaccharide. All right. General roles. Well, think for a second. What do you think the roles of sugars are? Leo, stop scratching the carpet. Oh my gosh. You're going to get, hopefully, if nothing else, you'll be abused while I'm doing this because my cat, when he doesn't get the attention he thinks he deserves, he starts getting kind of mischievous. So we'll see what he does. All right, well, back to the task at hand. What are some general roles of sugars? All right, well, probably an easy one that you can think of is energy, fuel, right? Yeah, of course. Carbohydrates are important energy sources. Carbohydrates have calories. That basically means they can be broken down to give off energy that the body can use. Right? However, that's not the only thing. Carbohydrates have rich and varied roles in biological systems. They can be important structural components. Right? Plant stems, wood, the shells on crustaceans and hard-shelled insects. All of those are actually sugars. You probably didn't know that. Kind of neat. A lot of the reactions and processes and signaling that happens on the surface of cells is due to some sort of carbohydrate binding. There are a lot of carbohydrate receptors on the surface of cells that can be bound to signal various biochemical metabolic pathways and other reactions that happen. All right, so let's start at the beginning, and the beginning is the most, I don't want to say basic because that always implies acid base, the simplest type of sugars. In fact, these are often called simple sugars. You may have heard that phrase before. These are the monosaccharides. All right, so I don't know that I put this picture in here. I did not actually put it in the PowerPoint, but if you take a look at page 455, if you have the same book that I do, figure 16.4, you can actually see many of the most common simple sugars that are used. And you'll see there's quite a few of them. In fact, you probably have heard of some of these. I'm sure you guys have probably heard of glucose, right? That's probably the most well-known monosaccharide. Fructose is another really commonly known one. Galactose. Blanking here. Ribose is another one. Xylose. We can go on and on. All right. If you look at that picture that I just highlighted, or even if you don't, I'm going to sort of scroll over here. And here, I'll just use this picture here. This is glucose. Look at the very top, all right? Think back to organic chemistry. What type of functional group is that? C double bond O with an H? That's an aldehyde group, right? All monosaccharides are going to have either an aldehyde or a ketone group, all right? So, just to refresh your organic knowledge here, this is an aldehyde. And this is a ketone, right? So, since glucose has an aldehyde, that's going to have a special type of classification, a special name. You're going to see there's a lot of lingo in this chapter. All right, so if a monosaccharide contains an aldehyde group, it is called an aldose. If it has a ketone group, it is referred to as a ketose. All right, so what does a ketose look like? Well, ketose is going to look something like this. Oops, sorry for that really raggedy looking bond there. My cat is meowing at me. He is displeased. Come here, Leo. All right. Here you can see the ketone group right over here. Carbonyl, and then two R groups on that carbonyl carbon, right? So this is actually fructose, the specific monosaccharide, but if you're looking at a classification of it according to ketone group, that's an example of what we call a ketose. All right, so all the common monosaccharides are going to have one of these two groups in them, okay? So that's one bit of terminology that you can use when classifying a monosaccharide. It's going to be either an aldose or a ketose. Also, you can classify it according to the number of carbons, all right? So, Leo, don't attack my hand. My cat is attacking my hand as I'm attempting to draw on the iPad. This is sad. This is my life. This is what I go through to educate all of you, so hopefully, yeah, you appreciate this. All right, so number of carbons, is 3, for example, right? Well, think of the common prefix that's used for the number 3. It's tri, right? All right, so it's tri, and then we add the suffix "-ose" because it's a simple sugar. It's a triose. If you have 4 carbons, it's a tetrose. If you have 5, it's a pentose. 6, it's a hexose. And I could keep going, indefinitely here. But these are the most common ones. All right? So, in addition to either being aldoses or ketoses, the simple sugars are also going to be, an ose according to the number of carbons it has. And you can actually combine them as well. For example, glucose. It has an aldehyde group. And it has 6 carbons. So it's not uncommon to refer to glucose as an aldohexose. Basically, you put the prefix for the functional group first, and then the prefix for the number, and then ose at the end. Fructose has a ketone and 5 carbons. It is a ketopentose, etc., etc. I have no idea how long I'm going to be able to make this first video because my cat is stalking me and he is mad. If you have ever seen a mad cat, you know, hell hath no fury like a feline scorned. Alright. Guess what's important here? Everybody's favorite topic, stereochemistry. I really like this chapter because there's a lot of good organic chemistry principles in there. So I have no doubt that you will love it as well. And everybody loves stereochemistry, right? So this is actually going to harken back a bit to what we looked at with amino acids, right? We saw that amino acids always had a stereogenic center. So you could actually have different stereoisomers of amino acids. And you might also remember that we didn't go according to the RS system. We used a different system called L and D, right? Now, no matter whether you're using RS or LD, you can still have the same, the same relationships between different basic structures just having different 3D arrangements, right? Sugars, simple sugars, they can have enantiomers. All right. Definitions in your PowerPoint, hopefully you remember, enantiomers are non-superimposable mirror images of each other. You can also have diastereomers, where they're non-superimposable non-mirror images. All right. There's another term to look at here, and that is called epimer, right? So let's say you have 2 different stereochemical forms of an aldohexose. If they differ only at 1 chiral carbon, then those are called epimers of each other, right? So, for example, let's say we had Leo, stop scratching the carpet again. This cat is going to be the death of me. Wow, I totally screwed up. What the heck was I thinking? None of these should have H2s there. Sorry, my cat was distracting me and threw me off. I'll just blame it on him. Tell you what, you don't know terror until you hear a bunch of mysterious noises and you know it's your cat but you can't see them. So, all right, so here's a couple of aldohexoses, right? So these would be epimers of each other, right? Because each one of the stereogenic centers that I'm labeling right now, those are exactly the same, but these here are different, right? Differ at only one chiral carbon, so they're referred to as epimers. You might notice the way I'm drawing these. Leo, stop. So, this harkens back again also to what we learned in the amino acids chapter. Since we're not using RS, we're using DL, we use a special type of system, and that's called Fisher projections. Now, we've talked about Fisher projections before. And I'm going to, if we look at this one right over here, again, you'll have to look at your full PowerPoint on a computer, but this is actually illustrating here, if you look at B and C, basically the two of the simplest types of simple sugars you can have, the smallest ones, right? Glyceraldehyde is a 3-carbon aldose, so it is an aldotriose, right? And it's going to have 3 carbons, one of which is stereogenic. All right, so again, I'll kind of draw this along here on the whiteboard so you can see it. All right, 3-carbon aldose, so the aldehyde groups drawn on top. Here's your stereogenic carbon. Here's your CH2OH. Here's your OH. And here's your H. Okay? All right, so we learned when we talked about amino acids that you actually drew 2 dashed lines coming out of your stereogenic carbon. One going straight up and one going straight down, right? And then one wedge on the right side of the stereogenic carbon and one on the left side. Those are ugly, but they'll do. Okay? So what we said was, with amino acids, if you look at the stereogenic carbon, if the higher priority group of the 2, left or right ones, is on the right, we said it was in the D configuration. And that's what we do here as well. Basically, when we look at the stereochemistry of a sugar, we're looking for the position of the OH group, right? So in glyceraldehyde right here, it's on the right-hand side on the wedge, so that's the D. If it was on the other side, it would be the L, all right? Now, this is not the only way that you can draw Fisher projections. Over the years, chemists kind of, I don't know if they got lazy or if just got more, if they started working smarter, not harder, and decided to get a little bit more efficient with things. But eventually, this kind of morphed into drawing the same type of structures, but with flat lines instead of dashes and wedges. So this is also a Fisher projection formula for diglyceraldehyde. In this case, really what it comes down to when trying to identify whether this is D or L, since we're so dependent just looking at the position, is it on the right-hand side of the carbon or the left-hand side, we actually don't even need the dashes and wedges. So This basically means the same thing, this drawing, as the three-dimensional one I just drew. So you're just looking at the position of this OH. It's on the right-hand side, so it's D-glyceraldehyde. Okay. Now, let's say you have something bigger than 3. Let's say you have 4 or 5, 6, whatever. Let's look at a hexose. Let's look at good old glucose right over here, and you can see glucose. Let's look at part B, right? D and L glucose. All right. Whenever you're looking to determine whether a simple sugar is D or L, you might have several stereogenic centers. If you look at the structure of glucose here, either one of these, you're going to count 4 stereogenic centers, right? If you remember from organic chemistry, there was a mathematical formula: the maximum number of stereoisomers. Misspelled that. That can be present for a given structure, right? It was 2 to the nth power, and n equals, gosh, I cannot write tonight, n equals number of stereogenic or chiral carbons. That's really ugly, but you can see. All right, so if we go over here, if we look at glucose, right, D-glucose on part B, it's got 4 stereogenic centers, so theoretically you could have up to 16 stereoisomers, right? And that would come from the OHs on those chiral carbons kind of switching places and being in different combinations. However, only 2 of those are going to be glucose. And that's going to be these 2 that we have in part B. Look at the stereogenic carbon that has the highest number. That's going to be the important one for determining D or L. All right, so let me look at glucose. Come on. Okay, so this is D-glucose. First of all, let me address the whole fact of, this has 16 different stereoisomers, or the maximum, but only 2 of them are glucose, because it's only glucose if you have carbons numbered like this: 1, 2, 3, 4, 5, 6. The OHs on carbons 2, 4, and 5 have to be on the same side. The OH on carbon 3 has to be on a different side. That's the only case. If we had all 4 OHs on the same side, that's one of your 16 stereoisomers, but it's not referred to as glucose anymore. It's referred to as something else that I don't happen to remember. Oh, it's allose, A-L-L-O-S-E. Right? So, there's basically 2 arrangements where we have OHs on carbons number 2, 4, and 5, same direction, and the one on carbon number 3 in the opposite direction. The other arrangement would be this. Let's roll. Okay. Again, we start numbering. We start numbering at the carbon that has your aldehyde group. 2, 3, 4, 5, 6. That's how we number it. Okay? This, if you look at it closely, is the mirror image of the other one. Non-superimposable mirror image. Right? This is L-glucose. And these are enantiomers of each other. And these two enantiomers are the only ones that have the name glucose attached to them. If all four OHs were on the same side, it would be allose. If the OHs for 2 and 3 were on the same side, and then the OHs for 4 and 5 were on opposite to that, that would be mannose. And so forth and so on. All right? So these are the only glucoses. How do you know which one's L? How do you know which one's D? What you do specifically is look at the position of the OH on your highest number stereogenic carbon. We don't care about any of these or any of these when doing L and D. We only care about the position of the OH on your highest number stereogenic carbon. On this one right over here, it's on the right side, so it's D. Over here, it's on the left side, so it's L. There you go. It's a very systematic system. That's a great phrase. It's a very systematic process. A little tricky at first, but once you get the hang of it, it's actually very, very predictable. And that's kind of nice. Okay. One thing that's kind of interesting. Did I not put this in here? One thing that's kind of interesting is that most naturally occurring sugars I guess I shouldn't say sugar, I should say monosaccharide. They're in the D arrangement. Yeah, you don't see a whole lot of monosaccharides in the L arrangement, at least not in nature. They exist. There's a few of them in nature, and also we can synthesize them in the lab. We can't digest them, though. Kind of funny. Yeah. We cannot digest L-glucose. We can digest D-glucose, though. All right? So there's actually an enzyme called hexokinase. All right? And hexokinase is going to be an enzyme that's basically it's the enzyme in the first step of glycolysis, which is basically the breakdown of glucose. All right? If you remember when we were talking about enzymes and all, we said that, when the peptide chain, the protein chain, winds around and creates, its active site where the substrate actually comes in, the shape is very important, right? These pockets are going to be essentially themselves chiral. So the 3D arrangement of the incoming binding substrate is going to be important. Hexokinase, it can bind D-glucose, but it can't bind L-glucose. So, if we consume L-glucose, it's not going to hurt us. We can consume it. It's not poisonous or anything. But, ow, Leo, my cat is attacking my feet. Sorry about that. That was scary. Anyway, Since L-glucose can't be bound by hexokinase, it can't be digested, right? It can't go through glycolysis, so it just passes through the system. In fact, L-glucose in the past has been used at times as a laxative because it goes straight on through and it carries stuff with it. I don't think it's used that much right now, though, because this actually costs quite a bit of money to produce L-glucose. So I think most of the pharmaceuticals manufacturers have found it's really just not worth it. So there you go. Interesting bit of fact. Hey, Leo. All right. So one thing that's really cool about certain monosaccharides is that some of them will actually cyclize. They can react with themselves to form a ring. Not all of them do it. Just basically certain 5 and 6 carbon monosaccharides. Right? And they can form what we call hemiketals and hemiacetals. My cat is giving me a death stare here, so if this first video is pretty short, I apologize. In fact, I apologize. I feel a little unprofessional for doing it like this, but I've been really pressed for time, so I've been trying to really budget time, carefully, and I tried to double dip and give my cat attention and do this at the same time, but it's not working. So I'm going to cut this one short right now, and then I will do another video shortly that will pick up right where I left off, and we'll talk about cyclizing some monosaccharides. Until then, I'll talk to you later. Bye-bye.